All right, I'm going to go back to the dodecagon with perimeter of 108 centimeters, excuse me. I'm just drawing that base triangle again and looking at the right triangle that's formed when we draw the apothem in. We found that the degrees of the central angles of the dodecagon are 30 degrees, which makes the angle in our right triangle 15 degrees. And then this is 30. We really want to know that apothem there. We need an angle or a side first, and we found that since the perimeter is 108, if we divide that by 12, which is the number of sides, we find that each side has length 9, so that's the whole side. And so just this edge of our right triangle would be 4.5. So I'm going to make a tangent ratio to that to find x. The tangent of 15 degrees, tangent is opposite over adjacent. The opposite side is 4.5 in our right triangle, and the adjacent side is x, which is also the apothem. And we're going to swap the tangent of 15 and an x and have x equals 4.5 over the tangent of 15, and that will equal approximately 16.8. So that's going to be x, which is also our apothem. To find the area, we need area is 1/2 the apothem times the perimeter. We said the apothem is 16.8. They gave us the perimeter of 108, and we'll just put it in our formula. So that 1/2 of 16.8 times 108 is our solution, which should be 906.9 centimeters squared. Okay, and then we have problem number 11. It says find the area of the trapezoid. We have the formula for the area of a trapezoid is area equals 1/2 base 1 plus base 2 times the height. So we need to have those values. We do have one of the bases. We need to find the height in the other base, and we're going to do that by using our right triangle. This is a 30, 60, 90 right triangle. I'm going to draw a better version of it down here at the bottom. And let's see, this is 60 degrees. We have a 30, 60, 90. And this is 2. In a 30, 60, 90 triangle, the side opposite 30 would be represented by A, the hypotenuse is represented by 2A, and the side opposite 60 is represented by A square root of 3. Do a little math there and divide by 2. We find out that A is equal to 1, which is this side. And then the side opposite 60 would be 1 square root of 3, or just the square root of 3. So there's the hypotenuse, there's the side opposite 30, there's the side opposite 60. And we can put those back in our triangle that we have. Again, this is 1. The height is square root of 3. And if this whole thing is 13, then we have a side that's 1, and then we also have a side that's 12, because 12 plus 1 is our 13. And so the opposite base would also be 12 then. And we want to see what we can fill in our formula. We need base 1, we need base 2, we need the height. Base 1, I'm going to make that our top base is 12. Base 2 is 13, and our height is the square root of 3. So I have 1/2 of 12 plus 13 times the square root of 3 for our area. You simplify that, you leave that in radical form as 25 square root of 3 over 2, which is what it asks for, but also if you give it in decimal form, you get approximately 21.7. Number 12 asks us, it says the dashed triangle is a dilation image of the solid triangle. What is the scale factor? This is something we didn't really talk about, but this goes along with our translations, and I think it's a pretty easy concept. All I'm going to do is take corresponding sides of my figure. I have the side of the solid triangle has 1, 2, 3, 4 units in width there, and then the corresponding side of the smaller triangle is 2. And it says the dashed triangle is a dilation of the solid. So basically we started out with the larger triangle, which we're going to show our corresponding sides of 4, and then that went down to 2. And so basically what happened is we took half of 4 is 2. So the scale factor then would be 2 over 4, or 1/2. Okay, on number 13 it says the dashed triangle again is a dilation of the solid figure. So you can see that the dashed figure is smaller than the solid figure. We're shrinking it down, so it's going to be a fraction of the larger triangle. The last time we kind of counted the sides, and on this one the easiest way to do is to actually count the height because we're going by units. And you can see the large triangle has a height of 6 units, and the smaller triangle has actually a height of 2 units, and that's what I'm shrinking it down to, from 6 to 2. So this dilation is going from 6 to 2, or a scale factor of 2 over 6, which is 1/3. Now it's asking also about the center. And the center, it's really easy. We're just looking for what's right in the middle of that height. The middle of the height of 6, we're going 3 units in, and 3 units in from the left, 3 units in from the right, is at the origin. And it's the same thing for the smallest triangle, except it's 1 unit in from the left and 1 unit in from the right. So the center is at the origin. The center is 0, 0. Number 14, it says find the length of the missing sides in the triangle. It says write your answers as integers or as decimals rounded to the nearest tenth. If you take a good look, you've got a 45, 45, 90 right triangle. We're just going to use that knowledge. Hope you remember it. If not, you can always use a trigonometry function, sine, cosine, tangent, to help you find out what x and y are. If I have a 45 and a 90, this is also a 45 degree. And with a 45, 45, 90, each of the legs is represented by a, and the hypotenuse is represented by a square root of 2. If one side of a, where we have a leg that's equal to 3, so a is equal to 3, therefore the opposite leg has to be 3, which means that, of course, y is 3. And for x is equal to a square root of 2, and we know that a is 3, so x must be equal to 3 square root of 2. Nope. And it did say write our answer as a decimal. And so x is approximately 4.2. On number 15, this is something that we've done recently. It says find the measure of angle BAC. So I like to highlight whatever I'm going to find. I want to find the measure of angle BAC. We're only given one angle, so we have to use what we know. Just because we're given one angle measure, we also know that a semicircle is 180 degrees, which we have a portion of that there. So angle AOC is 180. We have 84 degrees, so we're going to take 180 minus 84. And that will give us 96. And that would be the angle of measure of angle BOC. The central angle and the arc formed by that central angle have the same measure. So arc BC also has a measure of 96. And you can see that angle BAC also forms the arc BC. So they share the same arc. But when we have an inscribed angle like BAC, that measure of that angle is half the measure of its included arc. So the measure of angle BAC would be 1/2 of 96, which is 48 degrees. All right, for number 16, we have an intersection on the outside of the circle, which is angle A. And we have an arc DE, which is 97, and an arc BC, which is 40. And the formula for that is the measure of the angle of intersection is equal to 1/2. When it's on the outside of the circle, it's the difference of the arcs that are created by the angle. So 97 minus 40 is 57, and half of that would be 28.5, I believe, degrees. On number 17, we have an intersection on the inside of the circle this time. It's very similar to what we just did. We want to find this time the intersection in the middle, which is angle X. AB is 35, CD is 34, and instead of finding the difference this time, we find the sum of the arcs that are created by the intersection. So we'll have 1/2 of 69, which is 34.5 degrees would be the measure of angle X. Number 18, we want to find the lateral area of a cone. Again, we have a formula for that. Lateral area is equal to pi times the radius times the slant height. So we need to find the slant height of our cone. We have a right triangle here. This is going to be 30 meters because the entire diameter is 60, and then do the Pythagorean theorem to find the slant height. So we have L squared, I'm sorry, let's back up there a little bit. 30 squared plus 40 squared equals L squared. And if you work that out, you'll find that L is actually equal to 50. And we can fill in our formula then. We have pi, we have the radius, which was 30, and then the slant height is 50. And that gives me a value of 1500 pi, which simplifies, so scoot that down here just a little bit, to 4,712 meters squared.